Hello, this is Mr. Waters, and here is our first lesson video. Okay, and we're going to be talking about going further with sequences today, and including something called a geometric sequence. But what that means is we'll get to in a minute. But first, I want to consider this situation that we had previously, where we were buying hamburger, and we dealt with this. We had this a kind of an activity, or at least a scenario where we were buying hamburger, and we related to the idea of transformations in linear functions. But in the world, let's say that you were at a store buying hamburger, right? And let's say that the hamburger was $5 a pound, right? Well, 1 pound costs $5, 2 pounds cost $10, 3 pounds cost $15, 4 pounds cost $20, right? And then, and so on, right? And now you want to see this. Before, we saw that as a linear function, where p of x was equal to 5x, right? And because that was a slope and so on, right? And we could use this equation to predict how much, 100 pounds of hamburger would cost or whatever. But in terms of what we're doing now, you can see this also forms an arithmetic sequence. And we know that it's an arithmetic sequence because each subsequent term in the sequence has its same difference of 5, which we called the common difference. And where the position number n was the number of hamburgers, number of pounds of hamburgers, and a sub n were the pounds of hamburger, right? Okay, so this shows us that our arithmetic sequence is actually, as we said before, a special kind of function, where the position number in the sequence is the domain, right? But with the specification that the domain number has to be a counting number. 1, 2, 3, 4, 5, 6. Can't be a fraction, usually not 0, and never negative either. Okay? All right. So that was our idea of an arithmetic sequence. But consider the next situation we had, where we were playing. We had this activity in which a chess player, two people were playing chess. One was a peasant who defeated the emperor, and his prize was he requested 3 grains of rice on the first chess space, and then a number of rice grains double to that on each subsequent space. So the second space was 6, third space was 12, fourth space was 24, the fifth space was 48, and it didn't seem like much in the beginning, but there was going to be double of the amount on each chess space until we got to the last space on the chessboard, which was 64. In terms of a sequence, you're going to see this as the 64th space in the sequence is the amount of rice that was on the 64th space, right? Okay, so anyway, so is this an arithmetic sequence? So this is a kind of sequence. You can see there's definitely a pattern there. It's doubling each time, all the way until the 64th space. But is it an arithmetic one? Well, no, not really. As you can see, if we calculate the common difference, 6 minus 3 is 3, 12 minus 6 is 6, 24 minus 12 is 12, 48 minus 24 is 24. Each one, that's not a common difference, right? Each one is different. So that's not an arithmetic sequence. Well, what is going on with this? Well, instead of subtracting, we're going to go ahead and see what happens when we divide. Rather than subtracting 6 by 3, we're going to divide 6 by 3. Since we saw that it was doubling each time, 6 divided by 3, 12 divided by 6, 24 divided by 12, 48 divided by 24, each previous value divided by whatever the subsequent value is. Well, we see that when that's divided out, look at that, each value is 2. So now there is something common to all of these pairs of values, but instead of a common difference, It's a common ratio. A ratio being a division of two numbers, right? And since they're all the same, we're going to call that the common ratio, right? And so each one of these so this sequence has a common ratio of 2, which in our formulas to follow is going to be called R. Just like the common difference up here was D, common difference of D was 5, this has got a common ratio of 2. Now, when we worked this last time, that led us to a formula looking like this, and we said, oh, that was an exponential function, right? We said, look at that. We called this an exponential function because the variable, the domain number, x, was in the exponent position, and the base number was a constant, right? In this case, 2. So we called that an exponential function, right? And we generated a formula for it that looked something like this, where g of n was the whatever the term was further in the sequence. G of 1 was the first term, r to the n minus 1. We use that to calculate the 64th term in the sequence, right? Because we put 64 in for n, and then and we worked from there, and we called this an exponential sequence. And we saw here that g sub 1 in this formula here, g sub 1 is the first term, which is 3. R is the common ratio, which is 2. So we use these two numbers here. We substituted it in for g sub 1 and r, and here's our formula here. And we use that to generate the 64th term in the sequence, which was here, 3, 64 minus 1, which was 63, and then we did on the calculator 2 to the 63rd power. Make sure you do the correct order of operations. Do the exponent part first. 2 to the 63rd power, which on Mr. Calculator we did like this. 2 exponent 63, all right? Hopefully you can see that. And it worked out to be this number here, 9.2 rounded off times 10 to the 18th power. Then we multiplied it by 3 and got 2.8 times 10 to the 19th power, which was, if you remember putting that in standard numerals, we would take this decimal point and move it over 19 times, putting in zeros to fill the spaces. And almost a huge and almost unimaginably large number of rice grains, a huge amount of rice, right? So this rice grain sequence here, the amount of rice grains on the spaces of a chessboard, was not only an exponential function, but a fine example of what we're going to call a geometric sequence. Any kind of a sequence where the subsequent terms are related by a common ratio instead of a common difference, that kind of sequence is called a common ratio. That kind of sequence is called a geometric sequence. Okay? Now, after that, we had another example, right? In that same activity, we said, oh, well, what if we had a radioactive element, right? We called it radioactive element Z, and we started out with 100 grams, right? And we still were working with geometric sequences here, and here's our geometric sequence formula. Remember, where R is the common ratio, that common multiplier, right? Which was doubling or multiplying by 2 on the last one, and G sub 1 was the first term in the sequence, or whatever the initial amount was, right? That's the first term in the sequence. All right? Okay, so in the case of radioactive decay, we said, oh, well, what if we've got, start with 100 grams of this element Z, and after a certain period of time, called the half-life, it's gone down to 50 grams, and after an equal amount of time, it's gone down to 25 grams, and after the same amount of time, it's gone down to 12.5. So that half-life is the time it takes, and for radioactive decay, it's always the same amount of time to reduce by 1/2, right? So this was, as you can see, that those amounts of radioactive element also form a sequence. That's the first term, that's the second term, that's the third term, that's the fourth term, and so on, as long as we have any of the radioactive elements still present. Well, let's see if it's a geometric sequence. We'll divide. All right? Remember, for geometric sequences, it's always the subsequent term divided by the previous term. So 50 divided by 100, 25 divided by 50, 12.5 divided by 25. Well, obviously, each one comes out to be 1/2, as you can see. And ooh, that's the common ratio. So it's a geometric sequence because each of those ratios are the same, right? So common ratio, R is equal to 1/2, right? Okay, well, cool. So that means we can write a formula to generate the nth term in this geometric sequence, or the amount of radioactive element left over after however many after however many half-lives you're interested in. So our formula, so you can see here that the common ratio is 1/2. G of 1, I better write that in purple. G of 1 is 100. That's the first term in the sequence. So I put 100 in the G of 1 position, and I put 1/2 in the R position, and here is our sequence. So right there, that's our sequence formula. Yeah? Okay, very good. Okay, cool. All right, so then, how much, what's the 30th term? So now we want to know what is G sub 30th, the 30th term in the sequence, or, how much radioactive element would be left after 30 half-lives. Well, we just, work it out on Mr. Calculator. 1/2, or 0.5 to the 29th power would be 1.9 times 10 to the negative 9, and then times 100 is equal to that, 1.9 times 10 to the negative 7, right? So that is the 30th term in the sequence. Okay, notice that with geometric sequences, if it's counting down, that is, if the values are getting lower, the common ratio will be a fraction. Okay? We called that a decay function when we were talking about exponential functions. If, on the other hand, if the values in the sequence are increasing, with exponential functions, we call that a growth function. But you see here, that just means if the values are growing with a geometric sequence, the common ratio R has to be something bigger than 1. Okay? Now, so that's that. Okay, so that's a geometric sequence. Now, what about this sequence here? How about this one? Okay, so this was like example 2, wasn't it? What about example 3? How about 2 and 6? Oh, 2 and 12. I want 2, 12. Okay, and how about 2 times, okay, and how about 40? I don't know, let's put a number down there. Okay, dot, dot, dot. Let's see, is there a pattern? And if there is one, is it geometric? Well, we're going to divide to get common ratios here. 12 divided by 2, that's 6. 18 divided by 12, well, that's 1.5. Okay, we can already stop because those two are not the same quotient. They're not the same ratio. This is not a geometric sequence. It may be a perfectly good sequence with its own pattern. It's just not a geometric sequence with an exponential pattern. So we would say no to this being a geometric sequence. Yeah? Okay, very good. So, now, on to ones that might be geometric sequences. So let's see here. Here's another situation. Okay, let me cover this up again so we don't see it all at one time. This will be actually, it looks like it's going to be example 4, huh? So I'll change that to 4. Okay. Let's say you're reading. There's a car that you're interested in, and you're reading about the way that it depreciates in value. Right. The car new cost $27,000, and according to the article about car values that you're reading, in subsequent experience shows that over the years the same kind of car would be worth $24,300 at the end of the first year, $21,870 the second year, $19,683 the third year, and so on. Okay. So what kind of, let's say we wanted to predict how much the car would be worth after 5 years, or after 8 years, or after 10 years. Would it have much value at all, say? Right? Would it have much long-term value at all? So we want to see that, as you can see, this is a sequence, isn't it? Right? That's the first term. That's the second term. That's the third term. That's the fourth term. What kind of sequence is it? Well, you can see if you subtract the values, it's not an arithmetic one. 24,300 minus 27,000. I'm doing it on Mr. Calculator here. That's equal to negative 2,700. All right, but then 21,870 minus 24,300, that's negative 2,430. Those two values are not the same, so there's not a common difference, so it's not arithmetic. Well, let's go ahead and see what happens. Maybe it's geometric. Well, so let's divide. Let's see if there's a common ratio. And oh, look, if we divide 24,300 by 27,000 even, we get 0.9. If we divide 21,870 by 24,300, we get 0.9. And if we continued going, basically we'd keep getting 0.9. So that means that, oh, this is a geometric sequence. So this is, yes, it's geometric. And how do we know it's geometric? Because it has a common ratio of 0.9. You should try that yourself to see if it's really 0.9. And R is equal to that common ratio of 0.9, right? So now, can we write a formula for it? In order to know what like the 8th term in the sequence could be or what the 10th term would be, we're going to need to know a formula, right? So here's our geometric sequence formula. And so where G of 1 is 27,000, right? And R is equal to 0.9. Now notice that that's less than 1, which is what we want to see with a geometric sequence that's counting down, right? Okay, so we put the numbers in here, 27,000 for G sub 1, 0.9 here, and then we want to know what if for the 10th year, we want to know what's G of 10, right? So G of 10 is 27,000, and then we just crunch the numbers on our calculator. Remember to do the exponential part first, then multiply by 27,000 at the end. So we do 0.9 to the 9th power times 27,000 works out to be $10,460.35 after the end of the 10th year. Okay? All right, very good. Now remember, this pattern that we see with cars and with actually virtually any other piece of equipment that you might have, like in your office, it depreciates in value over time, often at a predictable rate. In this case, it's an exponential rate, and that's called depreciation. Okay, so let's see here. Now let's try another example here. Now, I want you to see, is this one a geometric sequence? Well, okay, I'm going to cover that. Don't want to know yet. All right, good. Maybe you saw it already if your eyes were quick. Okay, notice this is a weird one because it goes 3, negative 6, 12, negative 24. So it counts and it flip-flops back and forth, right? So that's something you would never happen with an arithmetic sequence, but it can happen with a geometric sequence. So let's see here. Let's divide and see if there's a common ratio. Negative 6 divided by 3, 12 divided by negative 6, negative 24 divided by 12. And you see each time it's a negative and a positive dividing, and each time we're getting negative 2. So you can see these geometric sequences that flip-flop back and forth, where the common ratio is negative, and so we can see, oh yes, that's geometric. It's got a common ratio of negative 2. So we want to know. So in this case, we're going to want to ask the question: what's the formula for it, and what would be the 10th term in the sequence? Okay, very good. Okay, so we just start to plunk the numbers in here. 3 for the first term, negative 2 for the common ratio to the n minus 1, right? So that's our formula, 3 times negative 2 to the n minus 1. And then we put 10 in for n. G sub 10 is equal to 3 times negative 2 to the 10 minus 1. Well, 10 minus 1, which is 9. So that is going to be, I'm going to put a parentheses around this to make sure that I'm doing, notice what I'm doing here. I'm putting a parentheses around the negative before I put the exponent part on the calculator, because I want it to repeatedly multiply negative 2. I don't want it to multiply negative 2 and then make it, positive 2 and then make it negative at the end. So that's going to be 9. Boom. So that's negative 512. So that's 3 times negative 512, which is negative 1536. So G sub 10 is negative 1536. That's the 10th term in the sequence. Alrighty? Very good. Now I'm going to stop this video right here, and we're going to come back with some problems for you to try, as well as some other work with geometric sequences. Thank you.